Hi, AP Calculus. Sorry, I just got it started. We are waiting for a few more folks. Um, 1 second. So yesterday I did send out the recording on Remind, and if you go back to day one and day two, the slides, I'm gonna start to put the recording right here on the very first slide. So like right after today's done and it gets uploaded, I'll make sure I link the slides, link the videos into the very first part of the slides, which is slide number one for each day. So making that little adjustment to make sure we have access to the video recordings. But yeah, welcome y'all. If you haven't yet, you want to go to Google Classroom and make a copy of today's slides. We are on day three today. Welcome, welcome. We have a few more people coming in. Actually, a handful of folks coming in. Yay, that's great. Yeah, more. Welcome everyone. I was just going to go, sorry, I was just going over that videos will now be also linked on slide number one of our daily slides, if that makes sense. So for example, today's day three. Once I upload the recording, I'll just link it here back into our slides. So that way on Google Classroom, you have access to the slides. Just a little thing there to make sure we all have that. Cool. Welcome. Yes. Welcome to AP Calc. And it is April 13th. And our check-in question today is, what's your favorite thing to do when you are alone? And I am a tree right here. But anyways, what's your favorite thing to do when you're alone is our check-in question. Let's go ahead and think about this and put this into the chat. Okay, we got make money. We got read. Uh, awesome, awesome so far. Yeah, reading is the best one alone. I like to play music out loud. Like usually I play my music on earphones or something, but if no one's home, I just play it out loud. Yeah, listen to music, play music loudly. That's what I do too. Oh, and I like to watch shows. Yeah, me too as well. That's a good one. I actually like to watch my anime when I'm alone. I don't know why. Oh, we have cry, JK. Hey, that's sometimes sometimes a good cry is needed. We got listen to music, sleep, or watch some YouTube. Yeah, it's like those things you like to do and no one's home. I like this stuff too. I also like reading. I want to make some more time for that as a kind of like a goal for this, as a continuing New Year goal from January. Yeah, we got dance while listening to music. Love that. I like to pretend I know how to dance because I don't know how to dance. But in private, nobody will know. Awesome, awesome. Meditate or read. Yeah. Quiet activities, meditating or reading. Again, I still don't get meditation, but I feel like I really, really want to, and I should read up on that and or watch some stuff about it. Okay. Ooh, we got draw. Drawing is a nice one. Okay, y'all. Thank you so much for checking in with everyone here in AV Calc on what you like to do when you're alone. These are great. I resonate with a lot of what y'all wrote down here. Let's see. This is who we have missing here today. So I'm missing Kaylin with a K. Kaylin with a K. And is that it? I know I'm missing Sophia, but there's internet issues, I believe. So Sophia P. I mean. But other than that, I think I'm just missing Kaylin with a K. So just Kaylin with a K. If anyone knows how to reach out to the other Kaylin, feel free to reach out so we can get him in here. We get some credit today. By the way, I still need to input yesterday's Padlet credit. I haven't gotten around to it, but today I'll make sure I give some time to make sure I'm giving you your in-class credit. So don't worry about that. All right, thank you all for sharing. This is our agenda here today. I just took attendance. We're going to talk about Riemann sums today. I called it Riemann sums review. We did talk about Riemann sums in pre-calculus, but I'm going to make sure that I walk us through and make sure I fill in any gaps we have because it's been a while. If we get to it, we'll talk about sigma notation, check out, and then a little reminder that our next asynchronous, this one is due tomorrow at midnight. And after today's lesson, you'll be able to actually do that asynchronous. If y'all haven't checked it out yet, what this asynchronous assignment is, it's actually a Google form based on today's lesson, reviewing Riemann sums. So it's a Google form. This is due Wednesday midnight. You can feel free to do it right after class today, whatever works for you all. Let me know, does anyone have any questions about today's agenda or anything coming up for you? I'll pause and make sure I give some space for that. All right, cool. So it looks like we're all set. Before we jump into talking about like our Riemann sums review, let's do our recap. So we met up yesterday and we talked about the power rule for antiderivatives. Another word you see here is power rule for integration. Again, we're going to learn more deeply about what the symbol means more than just being an antiderivative symbol. So we had a little shortcut rule. We did some examples using the shortcut rule yesterday. And then after that, what we did is we talked about what happens when we have a curvy rate graph. And then you all went onto a Padlet and tried to put down your ideas on what we could do. And I asked you guys to think about what strategies we can use or what is something you can remember. So that's where we left off yesterday. And also popping up right here is a little screenshot of that Padlet where we put our ideas and also where we put things we perhaps remember. So we do have some remembrance of something we did last year. It was mentioned up here, or there was different ideas such as like isolating each point and yeah, remembering something like last year, or there was another idea where you could kind of find like the difference between two numbers and get like the middle and kind of make an approximation. So those were some ideas that were coming up when we thought about this. Like, what can we do if we have a curvy rate graph? How do we find the area under that? And then from there, be able to kind of interpret whatever that area means. So that's where we're heading to today. So some of you mentioned that thing we did last year though on the Padlet, and I see it mentioned here, and there was another contributor who mentioned it specifically. They said something about left and right rectangles. That's what we're going into today, y'all. Da-da-dun, Riemann sums. That's the left and right rectangles that was mentioned by your classmate and the Padlet. So today we're going to focus on this thing called Riemann sums. Our learning target today is I can review Riemann sums and apply it as a strategy to approximate areas under curves. Again, so we're reviewing areas under curves because this is going to lead us into the fundamental theorem of calculus. That's where we're heading to in this unit. Let me just pause so y'all can read and internalize the learning target here. All right, awesome. Welcome, welcome. If you just came in, we're just starting with the lesson, so just in time, awesome. Let's go on to slide number 6, everyone. Again, as a reminder, our slides are on Google Classroom and I am on slide 6. Let's talk about what is Riemann sums again. So Riemann, what is that? First off, Riemann is the last name of the man who used this approximation method to find areas under curves. If you want to look him up. His name was Bernard. I don't know how to say it, Bernard or Bernhard Riemann. So you can look him up and see the work he's done and contributed a lot to the calculus field actually with this idea. But anyways, that's where the name comes from. That's why we call them Riemann sums. So Riemann he used different kinds of rectangles to approximate areas under curves. And we basically use his methods today. And we even use the computerized method as well to make precise calculations of areas under curves with the help of calculus. Visually, as you all can see here, um, the more rectangles you have, the better your approximation of the area under the curve. So the more rectangles you draw under your curve, the better your approximation of the actual area under the curve will be. Again, you get a better approximation when you have less of the white space that's left over under your curve, or sometimes the rectangles go too much over your curve, some too under. But again, the more you use, the better you get at your approximation. So that is what Riemann sums are. And I'm going to go ahead and move us on to slide 7. So I gave you a little bit of an introduction of what is a Riemann sum. Now, I'm going to have you all do a Padlet notice or wonder of what I have right here on this slide. So there are different kinds of Riemann sums. There you have a left Riemann sum, you have a right Riemann sum, and you have something called a midpoint Riemann sum. You also have additional things I want you to kind of right now read it and look at it independently and kind of just try to sense make this. Don't forget to look down here to these little like little keys. I think you call those keys to kind of identify what certain symbols mean. So don't forget to look down here. But what we're going to do is we're going to pause and I want you to look at this slide and we're going to write down a notice or wonder on the Padlet. So for those on the slide, the Padlet is right here in the notes section, right here. Oops, get that Padlet back for us. And we're going to go on to the Padlet and we're going to again look at this slide and put down a notice or wonder that we have coming up for us. So I'm going to go to the Padlet to make sure first off that the Padlet is updated with you. So let me go with you and let's see where we're going to head to. Okay, awesome. So yesterday we did columns 3 and 4. If you haven't done that, please do that so I could enter in the credit. Right now we're going to go into column number 5. We are doing a notice or wonder on this slide right here. And you can click on it and make it big for yourself. Let's go ahead and have about a minute or two. I'll put the directions in the chat. A few of us are still finishing up our thoughts on this notice and wonder. Let's go ahead and have a few more seconds on this, and then we'll take a look at what we think so far about what we see on that slide. All right, I'm bringing us back so we can check out what y'all thought. Actually, a reoccurring theme I noticed as I'm reading through this is that a lot of you are mentioning that midpoint one, the one where it's called a midpoint Riemann sum, is either I see it as either being a combination of both right and left, and then some of you are saying that the midpoint seems like the best estimate so far. We also have some noticing is about the um, left Riemann not going over the line and the right going a little bit over. I notice that they're all positive, and if they were negative, are they different? That's a good wonder. That is a good wonder. Yeah, so there's a lot of mention about the midpoint being the best method. Um, I like this notice about the fact that almost all of them have the same like equation that's right at the bottom, except for that I equals part. And noticing is about the left being always kind of like underneath. I like that. I like these notice and wonders, y'all. These were very deep. Some of you are still writing, so please go ahead and finish up your thoughts. This is great. So I like how that was noticed. So today we actually won't get to talk about what y'all think is the best estimate, which is your midpoint one so far, right? Today we are going to be talking about reviewing Riemann sums, but we're going to talk about the left. The left, the way you do the left, the process is nearly the same as the right, but we're going to go ahead and talk about what makes something left versus right and so forth today. And then we'll make some connections. So yay, thank you so much for that, y'all. Let's jump back onto our slide and let's begin this review. I'm gonna go to slide number 8, everybody. So slide 8, y'all. We're gonna do an example together, and we're gonna take a look at the left Riemann sums. You notice how I also called it a left endpoint rectangle, whatever works for you all. And we're trying to approximate the area under the curve of, I know the function is written here, so let me write it. So this function is y equals x squared. And we're trying to approximate the area from between 1 and 3. So we're trying to approximate this area here. In between the two lines I just wrote. So if you want to envision this better, let me use a highlighter and I'm going to color in what I'm talking about. So area under the curve means this whole yellow part. I'm trying to shade in that whole area under the curve. So if I was to truly find the true area, it would be this whole yellow portion. Okay, so that's how we're starting off. And let's go ahead and take our little notes on the side. So one way to estimate the area under some curvy graph is to draw rectangles underneath them. These rectangles are our Riemann sums. So in the visual to the right, we're using rectangles to estimate the area under the function y equals x squared, which is equivalent to f of x. And it's between x equals 1 and x equals 3, as you can see here visually. Ooh, one thing I want to make sure I don't have is we didn't say this part. So you know what I mean? Like it's between exactly 1 and 3, not between 0 and 3. So this is white. Like if I was to use the eraser, my whole highlight would get erased. So this is white. So imagine I didn't color code this there. So it's just between 1 and 3. So for me right now, I'm just adjusting my mathematical precision. We want to make sure we're being precise. Let me just draw my line. Yeah, so it's just this yellow area between 1 and 3. Okay. Next, in order to be precise, I was just talking about precision, but in order for us to be precise, we're going to be using our function. Let me circle our function once more. We're going to be using our function right here to determine the height of each rectangle. So what do I mean by height? For example, the height of this first rectangle is 1. Cool. The height of the second rectangle, you got to be careful. It looks like it would hit 2, but it's actually slightly above 2. And that's why we need our function to determine how high is the rectangle actually without us making an estimate. The second rectangle, I think, hits directly at 4, though, luckily. So that's nice for us. And then this last rectangle, I think it hits right above the 6, I think. Again, if you want to use, if you have a ruler, you could see this, and I'm trying my best, but notice that. So these two rectangles go a little bit above, and when we're trying to estimate areas on the curve, we want to be precise. And how we are precise is by using our function to figure out the exact height of each rectangle. So that's what I mean with this bullet. Next, I want you to notice that in this visual right here, the base width of each rectangle is about 0.5 units. So let me draw that in. So base width, let me color that in blue. Base width, 0.5. What do I mean by that? So I mean this width right here. So the first rectangle width, since it goes halfway between 1 and 2, that means this width right here is 0.5. And then the second one's width is also 0.5. When it comes to these rectangles, they actually always should have the same width. If you have different width rectangles, that's just going to make life very hard. If they all have the same width, then it's going to be easy for you to kind of calculate the area of all of those rectangles to make your estimate. So again, all of these have a width of 0.5. Awesome. And then was our last bullet? Yeah. So these here that I have, these are called left endpoint rectangles, or you could call them left Riemann sums. Notice that these are called that way because their upper left-hand corner of the rectangle, see the upper left-hand, it's right here, is touching the curve of the graph. That's what makes this a left Riemann sum or a left endpoint rectangle, because the upper left-hand corner is touching my curve. That is why it's called like that. So let's go ahead and process all this information we have on this slide, and let's see if there's any questions. But what's going to happen after this is we're going to go ahead and start to calculate the area of those rectangles in the next slide, and we're going to make an estimate for the area under the curve as a little bit of a review there. Okay. I mean, it sucks to delete or to erase the annotations I did, but I mean, I am recording this, so this will be available in video. But I'm going to go ahead and delete my screen so that we can move on to the next one. Oh, actually, I think the next slide has a little bit more additions. Let's take a look. Let's see. Slide number 9, everyone. Okay, so slide number 9 just gets us to kind of outline or list off what in the world do we need to calculate the Riemann sums. Well, let's list it off. We need rectangle widths. Prior to this, we just saw that our rectangle widths were all 0.5. Cool, we got that. We need our heights of the rectangle, right? We need our heights, and this is usually the y value on our graphs visually, and we sometimes need to use our function to get precise with what the height is. So yes, we got how to get the rectangle heights, awesome. And we need to remember that once we have the area of each rectangle, you take them and you add them all up. That's what we have to remember to do. Add up together the whole sum and you get your approximation. The last point, which perhaps could be a new one to us all, is I'm sorry, that one's not new. We need to remember the units of any. What I mean by that is like, what are the units? Um, Last year, when we were trying to calculate how long Rapunzel's hair was going to be, whatever, um, what I had given you was a rate, and the area under the graph determined the amount of hair in that case. That was like the scenario. So just remember, if you have units, try to interpret what the area means. In this case, though, right now, we don't have any units. You don't have to worry about like what the area actually means. Right now, we're just going to review this skill. Lastly, this one's the part that I was mentioning might be new. Subscript notation. I don't know if you all noticed that there was a bit of a subscript when you did the notice and wonder. Some of you mentioned about the I. So something like you saw something like this, X sub I, that is subscript notation. So we use subscript notation to organize the endpoints for segments on the x-axis. So it's just a way to organize like which rectangle we're looking at, what comes first, and all of that. So that's this is subscript notation. So that's the last point that I kind of wanted to bring up. Let me know, is there any questions about this before we jump in and get started on calculating that area? Okay, cool. It doesn't look like we have any questions. So I guess we're ready to get started. Let's do this. Let's see. Oh, okay. So first off, this is the same picture. I have my rectangles, and you can see right here in pink, I labeled each endpoint of each rectangle with a subscript notation. There we go. I tried my best to use the formal vocabulary. So what I mean by that is, for example, this first upper left-hand corner has this endpoint, and it's called x sub 0. Here's our second one, or the second kind of division has the endpoint x sub 1. Third one right here, that's going to correspond to the number 2, and that is denoted as x sub 2 because we started at 0, so the third one is now 2. And then this one here is going to be x sub 3. Now, in this particular problem, because x sub 4 is not an upper left-hand corner, we're not really going to use x sub 4, but that's just there in case, if we were to keep going on and on. But we're going to be using this one, this one, this one, this one, not necessarily that last one. So that is just a little explanation about our subscript notation right here. So it's just a way to organize like what's our first, second, third corner, basically. Okay, y'all, let us begin. And I put a lot of effort and color coded this, so let's do this. So let's first do, y'all see this? I color coded the first rectangle in green. Let's focus on finding the area of this green rectangle. So we know to find the area of a rectangle, all you got to do is have base times height. Well, we've already found that the base of each of this rectangle is 0.5. That means I just need my height. To get my height, you're going to take your first input right here. It's 1. I know I wrote on top of it, but 1 is going to get plugged into my function to get what the height is. So notice how I plugged in that first endpoint into my function. 1 squared is 1. Cool. I go to the side right here, base times height. 0.5 times 1 is equal to 0.5. And I put units squared because usually area is in squared units. So we don't have any units here. That's why I put units squared. So let me just make sure I pause. So this is my width of rectangle. And this was the height of the rectangle. So width times height or base times height, same thing. When you multiply this two, that gives you the area of that green rectangle. Does anyone have any questions about how I found the area of this green rectangle, the first one right here? Let's see, I'll pause and see if we have questions. Okay, and don't worry, we're gonna have a Padlet process check right after this so that you can continue to process this. Let's go ahead and look at the next rectangle. So the next rectangle, I'm gonna color code in, let's see what's the color. It is red. So I'm doing this next one now. So in this red rectangle, so I'm gonna have to kind of make sure I don't want this arrow to be in my way. I first off need to figure out what is my input actually before I actually move on. So what do I need to plug into my function? So my input right here. So it's right directly in between 1 and 2. So this number right here that corresponds to x sub 1 is 1.5, I believe. Let me know if anyone disagrees, but we need to plug in 1.5 into my function to figure out this exact height. So that's what I'm going to do next. And you're going to see that pop up right here in the side. I need to plug in 1.5 into my function. And basically you get 1.5 squared. So that's 1.5 times 1.5. Use a calculator, use, the internet. If you do that multiplication, you get 2.25 as the height of that red rectangle. And that makes sense. Remember, y'all, when I was showing you, I said this number is slightly above the 2. Well, now we figured, even though this looks more than above that, now we figure that this is actually 2.25. The height of this red rectangle is 2.25. So that makes sense visually if we look at the graph. Cool, we have the height, but we're not done yet, remember? To find the area of the red rectangle, we're gonna do base times height, or width times height. That's gonna come up here in red, right here. So base times height. If you do this calculation, you should get 1.125 units squared. Again, because we don't have any units. All right, so that is how I found the area for the red rectangle. Let's see if anyone has questions about that one. Okay, so let us keep going, y'all. Let's do this. We got this. Okay, next rectangle in blue. And we're going to repeat the same process. So the upper left-hand corner of this blue rectangle corresponds to the input of 2. So that means I'm going to take 2. I'm going to plug it into my function to get the height. And it's going to show up right here. See, notice how I took 2, I plugged it into my function. 2 squared is equal to 4. Then to find the area of this blue rectangle, I'm going to go to the side and do base times height. So 0.5 times 4, which is basically equal to 2 units squared. I have no idea why this is outlined by blue, but yeah, same thing though. Same thing as I've been doing before. Woo, yeah, this is a workout. All right, y'all, we got one more rectangle to do. Again, feel free to use the chat or to pause me with any question if it comes up, or if you notice any error in my calculations, please point it out. Okay, y'all, we have the last rectangle to do. The upper right-hand corner of this last rectangle is corresponding to the number that's right in between 2 and 3. So that number appears to be, to me, correct me if I'm wrong, 2.5. Is that wrong? I see something in the chat. Yay, thank you, Russa. Yes, thank you for verifying that. So 2.5, cool. We're gonna take 2.5, we're gonna plug it into the function to get the height, which is gonna pop up right here. Let's see, what's that height? Oops, which is in purple. So 2.5, we plug it in, 2.5 times 2.5 gets me 6.25. So that's the height of this purple rectangle. Notice how that makes sense. It's a little bit above the 6, so 6.25 is the height. We're going to go to the side and calculate the very last area in purple. So 0.5 times that height, which is about 3.125 units squared. So what we've done so far is we have successfully now calculated the areas of all 4 rectangles. Remember, at the end of Riemann sums, you're supposed to add your areas up. So don't forget, a lot of times we're like, okay, I'm done. Well, no, you have to add up your areas to make your approximation, because remember, a goal is to approximate the area under the curve between 1 and 3. So add them up, double check my answer, but I got 6.75 units squared as my answer here. So you could totally double check my work there, everyone. And then we'll pause. I think we're done. We have used a left Riemann sum to estimate the area under this curve between 1 and 3. And right now, after I pause and after, if there's any questions, if there's no questions, we're going to jump into the Padlet and then go ahead and process check on what we just did right here. Sorry, just waiting for questions. My bad. All right, y'all, it looks like that we don't have any questions, so I'm gonna go ahead and clear my drawings. Let's jump onto the Padlet. I am going to slide 11. So we're gonna pause and Padlet, or pause and reflect. In your own words, I did a typo. In your own words, describe how we used a left Riemann sum to estimate the area just now. And I want you to think about if this was a good approximation or not. We're gonna be on the same old Padlet, but I'm going to go ahead and put this Padlet right back into the chat. Oops. And let's go ahead and think about this question here. We're going to go on column number 6, I believe, on the Padlet. So directions, column number 6 on Padlet. And we are right here, y'all. The very last column of our Padlet. In your own words, describe right now how in the world we use that left Riemann sum to estimate the area. And I want you to think about, did we make a good approximation or not, according to your opinion? And then we'll check in, y'all. Let's take about a minute or two on column number 6. Let's take a few more seconds to finish up our thoughts. And then we're going to come and take a look. We're on column number 6 on the Padlet. All right, everyone. I was just taking some time and processing what you all wrote. And it looks like, from what I'm seeing, right, it looks like the process, we understand that process there. A lot of you were able to kind of reiterate what exactly we did and how we needed to find like base times high, all of that. So that looks awesome. Two things were coming up. I did see a few folks saying that it was a good approximation, but then there was a few folks saying like, no, it wasn't good. It wasn't precise. I think I see it pop up right here. It says, this seems like a good way to approximate right here. This seems like a good way to approximate, probably not the most precise. Let me make sure I color code that. Someone else mentioned that too. Let's see, right here. Color code this one. So we made rectangles, but at the end of it, the estimate is not accurate because you're missing space that wasn't covered by the rectangles. So we have a little bit more details about why it wasn't precise here in that one. Let's see if there's anyone else who said it wasn't precise. Okay, then we still have a thought that's finishing up about it not being precise. Okay, right here, JM said, it feels like we're under approximating the answer. We have to get a closer answer. Awesome, awesome. Okay, so generally I was just highlighting those who kind of disagreed with it not being a good approximation. And yeah, we're gonna go ahead and talk about that. So some things that were mentioned was under approximating it and or the fact that there's these white spaces under the curve that we're not taking into account. So maybe I should shade it in so you all know what I mean when I'm saying the white spaces. And also what another student used that same phrase too, the white spaces, missing spaces under the curve. So it's kind of like we have these little triangles that we're not calculating the area of when we're talking about the area from 1 to 3, right? If we were to calculate these highlighted portions, we'd actually have a perfect approximation of the area under the curve. So that is what was meant. And I think that's what the other student had meant when they said, if we were to use this area approximation, we would actually be underestimating the true area or the real area under the curve. So yes, awesome, y'all. Let's go ahead and take this and lead us into the next portion. So let me clear up this slide. Thank you so much for your thoughts about this. And we're gonna go back to our slides, everybody. Just move the little screen. All right, so that was awesome. Okay, y'all, so we have this, boom. A lot of you, so I'm going back to this visual, everyone. Yeah, so usually if you have an increasing function, the left Riemann sum is going to under approximate the true area. If you have an increasing function, the right Riemann sum is going to over approximate the area. And some of you noticed that the midpoint was kind of in the middle as far as approximating. Yes. What I'm going to move and transition us onto now is actually talking about this part. I don't know if y'all remember sigma. I thought I added little circles here, but okay. I was going to do this. There we go. We're going to talk about this sigma notation, the stuff that's down here. We're going to have a brief little kind of recapping of what sigma notation is next in our learning to kind of just make sure we understand why we even need that down there and to just make basic connections. We're not going to get too complex with it. So that's what we're going to lean into next, y'all. So sigma notation. Do y'all remember this? I don't know, but if you don't, that's okay. Let's review. Let's review sigma notation. I am on slide 13. So what is that? So the Greek letter that looks like a weird, funky looking E is used as a compact way to represent sums. Whenever you're adding a bunch of stuff together, that's when we use sigma. AKA, if you're adding up a bunch of rectangles, then you want to use sigma notation to shorten up your calculations or to shorten up your work or your computations. So here's a little visual about the different parts of sigma notation. For example, whatever is the last value of your n term goes up here. Usually some formula goes in the front of your sigma. Where you start counting goes down here, and usually this number down here is called your index of summation. Take a look at this, let you process that, and then we're going to do an example. All right, y'all. So that is a little bit about sigma. Let's do a little example. So let's say I have this, and is there a question? There we go. There's the question. The question is, write the following sum in expanded form and then calculate the value of the sum. So this is basically a condensed way to represent a sum. Let me write that down because I said a lot of things. I said a big thing right now. Sigma notation is a condensed way to represent a sum. So imagine, y'all, if you're calculating like 100 rectangles, let's say you made 100 left rectangles to approximate some area. It's going to be horrible to look at 100 calculations. So sigma allows us a way to condensely show what you did as far as your work. So that's the Y on the sigma there. So that's another way to say what I just wrote up here. But let's do this, y'all. So we're going to start with our index. So your index gets plugged into your formula. So it says we start at 3, we end at 6. Let me show you what that looks like. Take a look, y'all. Notice how I started plugging in 3, and then I continued counting up on the integers until I reached the number 6. That is how I represent this in expanded form. See how it's expanded, it's not condensed anymore. So it is in expanded form now. That is my sum. But then it asks us to then calculate the value of the sum. Okay, that means I just got to go on a calculator, figure out what 2 to the 3rd power is, 2 to the 4th, 2 to the 5th, 2 to the 6th. So let's pretend I went on the calculator and did that. Of course, I went ahead of time and just input my answers here. So if you were to use a calculator and do this, this is what you'd get as your answers. Cool. So we got to now calculate the value of this sum. 8 plus 16 plus 32 plus 64. That is 120. So this is the end of this example. We have written this sum in expanded form, and then we calculated the value to be 120. Does anyone have any question about how I just showed in this example, how sigma notation was used, and any other clarifying questions about this right here? Okay, Cool. I don't see any questions, so let's get to it. I'm actually gonna go ahead. I'm taking a look at the time here, and we're gonna transition into our checkout today because I think that's as far as we can talk as far as our learnings. But we talked about a lot. Okay, so I appreciate you all. There was a bunch today. So again, we'll continue our discussion. If you're curious, you could check out the other slides. Asynchronous number 7, y'all, is due tomorrow, due midnight tomorrow, and it's basically a Google form that's about today's notes. So it's pretty straightforward. Just a little reminder on that. But anyways, y'all, our checkout. I want you to think about what is something, and it could be anything that I mentioned today, or even if you're thinking about something old, but what's something that you still need more practice on? Go ahead and put that into our chat for our quick checkout there. What's something that you just need more practice on? Okay, we got oh great. I love that mention. So mention of antiderivatives. We have I need more practice on sigma. I wasn't here for pre-calc on that lesson. Oh wow, you remember the around the time we did it? That's amazing though. I bet for me, because I barely get to actually teach about midpoint Riemann. Something I would need more practice on is about how to actually do midpoint Riemanns. Oh, okay, we see that popping up more. Yeah, midpoint equations. Definitely that makes sense because we haven't had that much exposure to that. Okay, so a lot of midpoints coming up. That's awesome. I agree. I agree. I need some practice on those as well, especially because they look like they make a really good estimate. Okay, okay. Any burning practice? Any burning last minute there? Not exactly practice, but getting a deeper understanding of the sigma notations of the different Riemann sums. Yes, and I encourage you to push yourself into getting that deep understanding for that connection, definitely. And we got antiderivatives and Riemann sums. Yes. Thank you all so much for sharing. Yay, I'm going to miss you all tomorrow, but I'll see you soon. Bye, everyone. See you on Thursday. Bye, y'all. Have a great day. See ya. Bye.